All right, physics reaction video number 64. You can divide it by 2 and divide it by 2 and divide it by 2 and divide it by 2. 64 is a fun number. Did a search for AP Physics this week. Here we go.
So now we are going to apply the idea of torque to a rotating system.
Fun.
And what we're going to see is that if we take Newton's second law for linear systems, which is F net equals ma, we can create a rotational analog.
Cool.
And what I mean by that is that these two situations are similar. Instead of writing F net, I'm going to write net torque. Instead of writing mass, I'm going to write moment of inertia. And instead of writing acceleration, I'm going to write angular acceleration. And
so I'm looking forward to this because the moment of inertia is such a hard concept. I mean, it ends up being this crazy calculation that has mass in it and square of distance, right? Which I guess you can motivate from the units. I'm trying to think. Yeah, and so but it's tough, right? But using this analogy is so interesting, right? Because you can say, well, what is M doing? How is it sort of mediating the response? Call this the response due to the external impetus, right? So it kind of depends how much mass you have to determine what your noticeable response is going to be. Sort of measurable distance changes to somebody who's trying to make you change your distance. And so from that perspective, it's this cool thing. But it's I don't know, it's just a lot harder to motivate just from its basic definition. So I'm really excited to see how she does this.
And so we can link torques to angular kinematics just the same way that we link
I like those straight
forces
lines.
to linear kinematics.
It doesn't always do it though.
One thing to pay attention to, the unit for torque, you may remember,
It's energy.
torque is force times the
joules.
lever arm. And you want to take the perpendicular components of those, but the unit is the Newton meter. Be careful that it's not the same as work. Work is a linear situation and torque is a rotational situation. So the way that we tell the difference is we look at the situation. We look at the situation to determine if it's linear or rotational. Let's try an example. A potter's wheel of radius 0.5 meters and mass 100 kilograms is freely rotating at 50 revolutions per minute.
That's heavy.
Okay, let's remember what we learned about kinematics.
So
we
it's
have a
meter
radius,
across.
0.5 meters. We have a mass.
Right, so it's a meter across. Can't even fit in my image here. So it's like a meter across. And it weighs the same as less than me. And it's rotating 50 revolutions per minute, so almost a revolution per second. So 1001, 1002, 1003. Okay, so that's got a lot of, how do we want to say it? Angular momentum, a lot of energy. And so the potter can stop the wheel in 6 seconds. Okay. By pressing a wet rag against the rim and exerting a radial inward force. A radial inward force of 70 newtons. An inward force? What? Sorry, I'm stuck on that because there would be no torque from an inward force, and that it has to lead to a frictional force. Okay, now I'm intrigued. This inward part has me intrigued. I think, because it doesn't look, okay. Ooh, yeah, it's way down here at part C. Man, that's pretty cool. Did you see how I was like, what? Inward force not going to do anything. It's got to be friction, and aha, sure enough, it's got to come from here. So let's see how they're going to do it. Okay, yeah, that's easy. Okay, so this, yeah, you can figure out how much because it took 6 seconds. Wow, this is a pretty cool problem.
100 kilograms. This is angular speed, 50 revolutions per minute. If I multiply by 2 pi radians per revolution, and by 1 minute per 60 seconds, I would be able to convert this. Let's see, it'd be 100 pi over 60, or 5 pi over 3 radians per second. The potter can stop the wheel in 6 seconds by pressing a wet rag against the rim. Okay, so we've got a change in time, 6 seconds. And exerting a radial inward force of 70 newtons. What is the angular acceleration of the wheel? And we have more information than we need to determine the angular acceleration of the wheel, but later on we're going to figure out
love
the
those
torque.
straight lines.
So let's look at our kinematic information here. We've got time. We want acceleration. This is our initial angular velocity, and we know that it's going to stop. The wheel's going to stop, so the final angular speed is 0.
Cool.
And now we can use a kinematic equation to solve it. The one I'm going to choose is that final speed equals initial speed plus acceleration times time. So 0 equals, oops, not 50.
So I'm really curious to see if she ends up calling this angular acceleration negative. I guess I would, right? It's slowing it down, but of course it has a direction, right? And so we're not even told which way it's rotating. So you might, counterclockwise or clockwise as viewed from the top, or maybe right hand rule up or right hand rule down. And so to me, there's just like an amount, but my guess is she's going to call it negative. And looking at this, the way this is set up, it's going to have to end up being negative. But yeah, I guess that, in the same way that when we do one-dimensional linear problems, we just use positive and negatives to indicate directions. The same thing's going to happen here, so that's pretty cool. I really loved how she said there's more information than we need here, right? She's only highlighted really just 3 of the things, well, just 2 of the things that she's given, right? She's highlighted this and this to be able to determine that. So it's like, okay, there's all these other scary things, but can you figure out just something simple? I'm actually wondering, do we ever need this 50 kilogram stuff? Yes, we do, because we're going to need the moment of inertia. So we're going to need both of these things to get the moment of inertia before we can do part B.
Gotta remember to use radians per second. 5 pi over 3 plus alpha times 6. I'd subtract 5 pi over 3 from both sides. Divide both sides by 6. And I get that alpha is equal to negative 5 pi over 18. Or if I put this as a decimal, let's see, 5 times
negative 0.9
pi divided by 18, I get negative 0.87
close enough
radians per second squared.
Or radians per second per second.
Okay, next question. How much torque does the potter apply to the wheel? Okay, so in order to...
So this is tricky, right? And you can already hear her pausing to try to marshal her thoughts, because students are going to look at their formula sheets and they're going to see torque equals force times distance. And they're like, oh, I got force, I got a radius, boom, done. 70 times 0.5, done, right? And right, that external force is providing no torque whatsoever. None. It's all coming from friction, which actually, if you're the type of student who doesn't read part C first, you'd be like, let's start cruising here. So I'm really curious to see how she sort of scaffolds and models for the students how to really think about this problem, because there's 2 ways to get torque. You either get at it from the torque equals I alpha, and we know alpha, and we got to figure out I so we can get torque, or torque equals force times the lever arm, distance, whatever you call it. And there's a force, and there's a lever arm. So I wonder, one thing you could do is calculate both and show they don't agree at all, or although they might be comparable. So this is a really interesting moment, especially for those students who haven't read part C yet. I'm just going to back up just a little bit.
Okay, so in order to figure this out, I'm going to say that net torque is equal to moment of inertia times angular acceleration. The moment of inertia, this object is a disk. So if I go back to my...
Wow. This image is so familiar to me. But, I mean, maybe she's using the same textbook that I taught out of. I just wonder if somebody is making money off of this image, because, man, this image looks familiar to me. The colors, everything. So I think I know which textbook it's from. I think, and for me, it's in the Young and Friedman textbook. I wonder about that. But this is so interesting, right? That you're like, oh, well, it's just this sucker, so let's use this. And someone might say, well, I don't think powder wheels are this thick. Oh, but the thickness isn't in there. Don't worry about it. But I actually think powder wheels have this big thing in the middle, or whatever. You know what I mean? This is what we're going to use. Interestingly, right, she didn't at all jump to that force times lever arm approach. I do wonder if she's going to come back around to it. My guess is she's really going to hit it hard when she gets to part C.
Pictures here. I'm going to use this moment of inertia. Solid cylinder or disk is 1/2 mr squared. Okay, up above, I did determine the mass and the radius, so I'm going to be able to put those in. And so let's do this. So I've got that the torque,
it's going to be
the net torque
10.
is equal to the moment of inertia, which is 1/2 mr squared, and then times alpha, the angular speed. So the net torque is 1/2 times 100
That's 50.
times 0.5 squared times
So 1/4 50 is 12.5.
negative 0.87.
So negative 10.
And I would put that into my calculator. And I get 10.9, pardon me, negative 10.9.
Nice.
And the units on that are Newton meters.
So compare and contrast to the other way that students might mistakenly do this. So it was 70 times 0.5. They would have gotten 35. So this is a third as much, right? A big difference. And so it's a really well set up problem to really indicate that approach is problematic. And then we'll see how she does proceed here.
Okay, finally, find the coefficient of friction between the rag and the wheel. Okay, so I'm going to make a sketch here.
That's so cool.
So what's happening here is that the person is pushing inward like this.
Nice.
Okay, they're pushing inward. Oops. With 70 newtons of force. But the force that actually is stopping this thing is perpendicular to that. The force of friction, remember that friction acts perpendicular to a surface.
Cool.
So if I were to look at a top view of this.
Yeah. Nice. Oh, that's so cool. I love the shape snapping. Oh, and that was cool too. Oh,
I didn't quite want all that.
that's cool
Get rid of
though.
these other bits. If I were to look at a top view, I'd have that F net going in toward the center, and then the frictional force would be perpendicular.
So let's talk about that copying and pasting, right? So when we're in a sort of lecture mode, it makes a lot of sense. The students really see the similarities, like, okay, I see what she's doing, right? It's literally the same exact drawing. But from the perspective of students taking notes, if they're not on a digital thing, right? Let's say you're encouraging them to do this on their own sheets of paper. That's hard for them to do. So now they might be spending more time trying to get their second drawing to look a lot like your first drawing, and whereas it took very little time for you because you did the cutting and the pasting. So I'm really curious about those sorts of discussions, right? I don't think there's a slam dunk here, right? Because the benefits of the fact that the drawing looks exactly the same is so hugely beneficial, and yet the potential moment of the students, frantically trying to catch up to your drawing might mean that they're not paying attention. So there's a really, really interesting trade-off there, and I'd love to hear what you guys think about that.
To the surface from my top view. The net force, because it's perpendicular, is also a normal force. Again, because this net force is perpendicular to the surface. We know that the force of friction is mu times the normal force. We know that the, we know that the normal force is 70 newtons. So what I need here is the frictional force.
Cool.
And the frictional force is what produces the torque.
Awesome.
So the torque was 10.9 Newton meters.
Does the sign matter? Probably not.
The force that I need is unknown, and the radius is 0.5. So when I divide this out, I get a force.
That's interesting. So she's sort of dropped the negative sign here. You can understand why, right? Because you don't want a negative coefficient of friction. So if you were to track these negative signs all the way through, we have said that the torque is negative. The torque is negative, and so that really just gives you an indication of which direction the torque. So she's saying it's that way, so that must have been spinning clockwise, right? It must have been spinning clockwise because this type of torque is going to get a clockwise spinner to slow down. And so there's the negative sign on this side is actually a much larger and harder conversation, even though instinctually the students would know which way it was spinning. So I think that by dropping the negative sign here and cruising through, she's going to get her mu to be a positive number. But I could just imagine the students saying, "No, it was supposed to be negative, and I was following along, and I got a negative coefficient of friction." And it's like, well, what does a negative coefficient of friction mean? Whoa, how'd you like to be on a surface that had a negative coefficient of friction, right? That sounds scary. So I'm really intrigued by that very subtle thing she did, where she just dropped this negative sign. Because really this is a magnitude conversation here. Oh, that's super cool.
Force of 21.75 newtons.
That was so cool. She shrunk it, moved it. Man, that's awesome.
And now I'm ready to solve for mu. Mu is going to be equal to
what is that? About point
FF over FN,
3,
which is going to be 21.75 divided by 70. Oops. Which is 0.31.
Close.
And remember that the coefficient of friction has no unit.
All right, just going to go back here. Wow, some super cool stuff. That's such an interesting problem that puts friction at the end. This negative sign stuff was fascinating. The shrinking the text and moving it was super awesome. The sign, sort of absence of a sign conversation totally makes sense, frankly, because it's really just a magnet. There's so many cool things here. And I think that what I didn't hear, because it sounds like it may have happened in another lecture, was really trying to push harder on what moment of inertia is, because we just sort of used it. But man, this was a really, really cool demonstration of how all of this stuff holds together. All right, everybody, have a great day, and remember, physics teachers are awesome.